All right, welcome. So in this video, let's continue our investigation of what it means for a set to be linearly independent or dependent. And let's consider some open-ended questions here. So let's think about we're in R3, so we're in 3 dimensions. Is it possible to give an example of a set that contains just one vector, which is a linearly independent set? So what it means to be linearly independent, we have this set S, which in this case is only containing one vector. And what we want to know is, does the corresponding vector equation x1 times v1 equals the 0 vector? If that only has a trivial solution, then the set is going to be linearly independent. So pretty much for any vector that I choose, this is going to be the case. So let me just pick the vector 1, 0, 0. For example, this vector is a linearly independent set with itself because the equation x1 times 1, 0, 0 equals the vector 0, 0, 0 only has a trivial solution, right? x1 equals 0 is the only way that we're going to get the 0 vector back. So now you might ask yourself, well, that means any vector that I plug in there is going to work. And that's not necessarily the case here. So think to yourself, can you think of a set of one vector in R3 which would be linearly dependent? And there's only one such set in R3. Namely, if I were to pick the 0 vector, this is going to be a linearly dependent set since the equation x1 times the 0, 0, 0 vector equals 0, 0, 0. Well, this equation over here has an infinite number of solutions. Anything I pick for x1 would be a solution. So the set that contains the 0 vector, this is not linearly independent. So if I'm considering sets of one vector, as long as that vector is not the 0 vector, that set would be linearly independent. And that's true whether we're in R3 or even if we're in higher dimensions. Okay, now let's jump up another vector. And so now let's consider sets of 2 vectors in R3. And let's think about, can we come up with a set of 2 3-dimensional vectors that form a linearly independent set? So let's consider a matrix equation where we've got x1 times v1. And I'm going to pick v1 to be this vector 1, 0, 0. And then we've got x2, and now we've got some place for a second vector. So if I want this set to be linearly independent, then that means I want to plug in a second vector over here so that this equation only has a trivial solution. And that gives me a lot of options. For example, the vector 0, 1, 0, the only way that I could take a combination of these 2 vectors and get the 0 vector back is, well, if the top entry is going to be 0, that means x1 has to be 0. And if the second entry is 0, that means x2 has to be 0. So this equation has only the trivial solution. So that tells me the set containing the vector 1, 0, 0, and 0, 1, 0, that would be a linearly independent set of vectors. We can similarly think about whether we can construct a set of 2 vectors in R3 that are going to be linearly dependent. So if one of them were 1, 0, 0, think about what vector could go in here so that when we take this combination of these 2 vectors, we get the 0 vector back. So first of all, note that if we have x2 equals 0, then that would imply that x1 would have to be 0 in order for this first coordinate to give us a 0 over here. So we're going to need both x1 and x2 to be non-zero. And if x2 is not equal to 0, that means its second and third positions have to have 0 in it. Otherwise, we would wind up with a non-zero term in the second and third position on the right side of the equation. So these 2 need to both be 0. And now I can see that picking some scalar multiple of the first vector is the only vector that's going to go over here. So I could pick any vector to be different. So a vector like 2, 0, 0 in the second position. Now we can find values for x1 and x2 so that when we combine these two vectors back together, we get a 0 vector on the right side. So if I have two vectors, one of which is a scalar multiple of the other, then that set of two vectors is going to be linearly dependent. And so now let's jump up to three vectors. Now we're going to have a set of three vectors in R3. And let's first construct a set of three vectors that are going to be linearly independent. And hopefully you're starting to get a little bit of a feel for these sorts of problems. So if I pick 1, 0, 0 as my first vector, 0, 1, 0 as the second vector, and then I can pick 0, 0, 1 as the third vector, and you can verify that there's no way that we can take some combination of these three vectors, picking non-zero weights, and wind up getting 0 on the right side. So this set S with 1, 0, 0, 0, 1, 0, and lastly the vector 0, 0, 1 is linearly independent. If we want to think of a set of three vectors that would be linearly dependent as we did in the previous one, well then if I pick the set S, which had 1, 0, 0 as the first vector, 0, 1, 0 as the second vector, recall that if I pick a third vector, which is some linear combination of the first two, so if maybe I take 2 times the first vector, 3 times the second vector, well, this set of three vectors would be linearly dependent since this third vector that we added is a linear combination of the other two. And lastly, jumping up to a set of 4 vectors. Is it possible to give an example of 4 vectors in R3 that form a linearly independent set? And let's take a look at the previous one. So in question 3, we had this set S of 1, 0, 0, 0, 1, 0, and 0, 0, 1. This is linearly independent. And so the question is, any other vector in R3 can be written as a linear combination of these three vectors. So any fourth vector that I add here is going to be a linear combination of the previous three. So there's going to be no vector that I can add to this set to give me a set of 4 vectors which is linearly independent. So in this example down below, this is not possible. And so if we are in 3-dimensional space, R3, the maximum size for a linearly independent set that we can have would be a set of 3 vectors. Any set that contains more than 3 vectors has no chance of being linearly independent.